Okay, so this is a continuation of our discrete probability distributions unit. We focused our last lesson on probability distributions of single events. In other words, what is the probability of all outcomes for single events? Okay. And the focal point for that, of course, was introducing the idea of this whole idea of an expected value, or a value that you expect to have on average for a single outcome. And now we're going to branch forward from that. Okay, just like we started with single probabilities, and then we went to, the ands, the ors, and then the complicated types of probability calculations. We're going to do the same thing here. What we're going to do is we're going to talk about repeated trials. So this is, if you remember back in our probability section, we did a section on independent and dependent events. Okay, and we are actually focusing on independent events today, and those are repeated trials, so repeated events that happen. In this case, multiple events really are independent events, but in this case, we're doing the same thing over and over again. Okay, and we're viewing it from a more broad perspective. And so in order to do that, a couple things happen. First of all, our expected value is not an expected value for a single outcome. It has to be an expected number of what we call successes, or number of times something happens. Okay, we call that a success. Of course, we know that when we do things repeatedly, it's not always going to come out the same way. It may come out another way, an unexpected way, or a non-desirable way, or a non-questioned way. And so as a result, we're going to have these things called successes and failures. Okay, and so we'll go over that idea as well here, and then of course we'll also go over an expected value, and as I said, that expected value will be the number of successes. But anyway, we'll get to that as we go along. Okay, so there's a few criterion to get used to. This is actually a nice lesson because it involves a probability of independent and dependent events. It involves probability distributions, what we're doing here, and it also involves our binomial theorem. This is called the binomial distribution, but it's in essence the binomial theorem. What we did way back when we were doing Venn diagrams and doing our set theory and learning about iterative processes and counting and so on and so forth. Okay, so it's a lot of things put together. So let's get started. First of all, this section and later sections are for repeated trials, and that's key. Okay, we're doing something over and over and over again. Now, whatever it is that we're doing over and over again, whether it's rolling dice for a board game or whether we're going for a drive, okay, whatever it is that we're looking at the probability of, okay, it's happening over and over again, and we're looking for the number of occurrences of a particular type. Okay, that occurrence of a particular type that we want to know the probability of, what we wish to know the probability of, is something called a success. Okay, a success. Success isn't necessarily a good thing. A success is what we want to know the probability of. If I'm an actuary scientist who's working for a car insurance company, a success would be someone getting into a car accident. Obviously, we know that's not a successful thing and a good thing when we use that meaning of the word. It's more successfully occurring. And whatever the occurrence it is we're looking for, it's been successful in occurring. Okay? So that's the idea of what establishes a success. And we can view anything as a success. Okay, whatever it is we want, whether it's heads or tails, whether it's rolling a 7 or not a 7 when we're rolling dice, or whether it's, getting in a car accident and not getting in a car accident. There's lots of things that can happen amongst those, but we just categorize them in one or the other, very extreme. So to go along with a success, we have not a success or a failure. Not a success, failure. Now, the probability of success is abbreviated by the letter P. The probability of a failure is abbreviated by the letter Q. Okay? And those two guys are actually combined together so that P plus Q always equal to 1. Because if you're successful and not successful, there's nothing else. This is basically the P at A, and this is P at A primed. That's in essence what it is. Okay, so that's what we're looking at. So let's look at this example and go from there. Okay, examples of the situation. I'm doing repeated trials. What is the probability of getting 4 heads when flipping a coin 7 times? So 7 times is my repeated trial. I'm getting 4 heads. What's a success going to be? Well, I want to know the probability of heads. So as a result, I am looking and I'm seeing that, well, heads is going to be a success. Okay, so what would a failure be? Well, you'd say tails. No, a failure is not a success. Okay, I know that it is tails, so it's the same thing. But you have to understand that it's not always going to be absolute like that. It's not always going to be for binary situations. It could be for rolling dice. If it's for rolling dice, and I want to know the probability of getting 7 5 times out of 8, then my success is a 7, which means my failure is everything else. Okay, so keep that idea in mind as you're going through this when you establish what a success and a failure is. So repeated trials, they can be viewed as success and a failure. Now, what makes it a binomial distribution is not the success and the fail. What makes it binomial is that we only have 2 probabilities, and the probabilities don't change. They involve these things called Bernoulli trials, and a key feature is independent. Remember how I told you that we're going to do independent and dependent repeated trials? This is for today. Today is all about independent. Dependent will be next day or next lesson. Okay? Again, 2 outcomes, success and failure, but just about everything we can view that way. Okay? And we're going to have repeated trials. Okay? Now, when do we use the binomial distribution? We use the binomial distribution when we have a specific number of trials. That's number 1. Those trials are independent. And then hopefully we're looking for a specific number of successes and so on. But really it starts with those 2 key features. So when I diagnose a problem and I figure it out, and I figure out the probability of an individual occurrence or multiple occurrences or the expectation, it's all based on the idea of repeated trials, success and fail, and that the trials are independent, which means the probability doesn't change. Okay? So we're going to look at the very first example that we did, although it's a little messy now. What is the probability of getting 4 heads when flipping a coin 7 times? So first things first, I've got 7 trials. I'm doing repeated trials. Now, in order to be able to use this crazy formula that's here, okay, I want you to understand the bits and pieces of it. So first of all, we have to know the number of trials, which is 7. Okay? Then we have to know, okay, well, can it be viewed, is it independent? Well, I'm flipping a coin. That's independent by definition. 2 outcomes. That's it. Okay? And it's a half and a half for each, roughly. Okay? So the probability of success and fail are going to stay the same. That means I can use my binomial distribution. Now, what I ask for myself is, well, what's the probability? What's the success and what's the fail and what's the probability of each? So getting 4 heads, I'm looking for the probability of heads. So a success is going to be heads, which is going to be 0.5. Or a half, whatever you want. For a fail, as soon as I know what successes are, I know what fails are. Okay, the probability is going to be not heads, which is also going to be 0.5. These guys have to add up to 1. Always. Success and fail. Okay? I also, in this case, am looking for 4 heads specifically. And so that's my number of successes. Which in this case equals 4. Now the way this works is quite simple. I know the probability of getting 4 heads is a half and a half and a half and a half. And because it's and, I get heads and heads and heads and heads. It's a half times a half times a half times a half. That's to get 4 heads. But I also have to get 3 tails. So that's a half times a half times a half times a half for the heads. A half times a half times a half for the tails. They all go together. So it's really a half times 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 a half. 1/2 to the power of 7, all put together for my 7 trials. What I don't know is how these heads and tails are arranged. So this formula is a marriage of those. So it's a marriage of a half times 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 a half, which is 1 out of 128. And it's also the number of ways in which you can do that. Remember, thinking about it, if I flip coins 7 times in a row, I can get heads, 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 heads. And then tails, tails, tails. Or I can go heads, tails, heads, tails, heads, tails, heads. Or I could go heads, heads, tails, tails, heads, heads, tails. Or I could go tails, 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 heads, heads. There's all kinds of arrangements. And all of those situations, all of those outcomes are all possible. So that order and the next order and the next order and the next order, they're all possible. So it's one or the other or the other or the other. Which means I'm adding 1 out of 28 together a bunch of times. How many times? 7 trials, 4 out. There's going to be all kinds of possibilities. So this formula is going to have 3 components to it. The first component is going to be successes. The second component is going to be failures. And then the third component is going to be the number of ways we get success and fail occurring. So it's got 3 pieces. So let me show you with this formula that I've already set up here with this situation again. 7 flips of the coin. 4 heads is what I'm looking for, which means I have 3 tails. Okay, so I build the formula. First of all, my random variable x is 4. Random variable x is always the number of successes. In this case, the number of heads, 4. Okay? Then what I do is I write down the probability of success. This is my success. And it's going to be 4 of them. And the probability is 0.5 or a half. I'm also going to have failures. There's going to be 3 failures. Notice that they total up to the 7 trials. The probability of that is also 0.5, but that is my fails. And they go together because it's success and fails go together for the total of 7. That's going to give me my 1 out of 128, or as a decimal, I don't know what that is. Okay? But remember, we can go heads, 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 tails, 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 or we can go heads, tails, heads, tails. All those possibilities. That's what this guy's for in the front here. It's a choose. It's 7 choose 4, what actually turns out to be 35. That means there's 35 ways in which we could arrange heads and tails where there's 4 heads and 3 tails. So this formula does all of that for me. Now, I would be taking this, counting all those possibilities and adding them all together. You know, all heads to start with and then tails to end with. That's 1 out of 28. Plus, all tails to begin with and then all heads at the end. That's another 1 out of 28. Or I can do repeated addition, which is multiplication, and the choose helps me do that. There's 35 ways in which that can happen. And we're not going to do that by figuring out all the possibilities. We're going to use the formula to our benefit. Okay? Now, as far as calculating this, I'll show you that in a second. Okay, so hopefully you understand where the formula comes from. I'll model that again as we're working through things. Okay, so next set of examples. Simple one to begin with. You roll a pair of dice 10 times. Okay, first of all, repeated trials. Yep. 10 of them. Second of all, dice. Well, dice, that's independent. They don't change. So I already know this is a binomial theorem question. Third, it says, what's the probability of rolling a sum of 7 3 out of 10 times? Okay, so I know it's 10 times. What's the probability of rolling a sum of 7 3? Okay, so can I view them as success and fail? And if so, what's the success? Probability of rolling a sum of 7 is what I want. So what's the success? Sum of 7. 7 is we can get a 7 with a 3 4 4 3 2 5 5 2 1 6 6 1 6 out of 36, which is 1 out of 6. Okay, reduced. It's a little nicer to use smaller numbers. My Q is going to, I don't even have to figure it out. You don't have to, it's a complement, right? 1 out of 6, 5 out of 6. These guys have to add up to 1. So it's what's left over. In fact, it's what's left over of the denominator from the numerator. It's a very quick, easy subtraction to do. Okay? The last thing I want to know is, am I looking for a particular number of successes? In this case, 3 out of 10 successes. So I do want 3 specific successes. So when I write P at x is equal to 3, really what I'm writing is, what is the probability of having 3 successes or 3 sums of 7 when I roll the dice 10 times? Okay? Then I build. Now you don't have to build. You can plug in the formula like a well-trained monkey. That's okay. That's what I did when I was your age. Because I didn't really understand it. I just did it and it worked and I was fine and blah, blah, blah. Okay, but to understand it, you want to build it. So these are my successes. There's 3 successes. These are my failures. There's 7 failures. And then I'm going to have a choose that I'm going to deal with later. The probability of success is 1 out of 6. Probability of failure, 5 out of 6. And then we've got a choose in the front. Now, to have 10 rolls and to figure out where those 3 7s are going to happen is just too crazy. There's a lot of different ways that can happen. 7, 7, 7, and then all the rest are different. Or it could be 7, a bunch different, 7, a bunch different, 7, a bunch, whatever. There's all kinds of possibilities. So I go to the choose. And the choose is quite simple. It's going to be 10, my number of trials, choose 3. That 10 choose 3 works out to be, I've got my cheat sheets over here. Okay, that works out to be 120. Now there's 2 ways you can calculate these. You can be very exacting. Okay, and keep all the decimal places in your calculator, and I'll show you how to do that. Or you can just sort of write down as close as you can and keep as many decimal places as possible. In the end, we round to 4. That's the standard that we use. And if that 4 standard is maintained and continued, then you'll usually be pretty good, okay, and pretty accurate. Okay, it's about how accurate you want it to be. That's a different story. Okay, so keep that idea in mind. I'm going to show you how to do it in your calculator. It's a little bit playful the way that I do it, but that's okay. If you're really good with what you're doing. Okay, so 5 divided by 6. Okay, it's the first thing that I do. I always do the biggest power first because that's going to be the most difficult number to calculate. Then I go y to the x to the power 7. 5 over 6 to the power 7. There it is there. Okay? And then what I'm going to do is I'm going to go times, because of course these are all multiplied together. I'm not even going to do the 10 choose 3. I've got the 120 there. That's good to have in your back pocket somewhere. So I'm going to go bracket, bracket. I'm going to go 1 divided by 6, because it's a non-repeating, non-terminating decimal, and you want to keep all those decimal places, to the power of 3, close your bracket, equals. Now that's these two guys multiplied together. And then, of course, I multiply it by 120, boop, and I get my answer, which is going to be 0.1550. And my closing statement, beep, boop, boop, you go on. Okay, so if you're good with your calculator, beautiful. If you're not good with your calculator, that's okay. Take it in baby steps. So I go 1 divided by 6 to the power of, oops, sorry, I got to be careful. 1 divided by 6 equals, to the power of 3 equals. Okay, so that's this guy. 0.004629629. I wonder if that repeats. Anyway, and you keep as many decimal places as you can. Then I go 5 divided by 6. And you can't just multiply this by 5. It's an exponent. Keep that in mind. Okay, 5 divided by 6. Y to the x, 7 equals. And there we are there. 0.279081647. Dot, 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 of course. Okay, but if you have that many decimal places, and then you do this times this times this, you'll get this. Okay, you round it to 4 decimal places. You're going to be fine. Okay, so it's up to you what you want to do. All right, so you go ahead and use the calculator as you wish, and I have a nice, beautiful set of calculations also posted for you, so you can look at those, making it look a little nicer. Okay, so P and X equals 3, okay, really means the probability of 3 sevens in a total of 10 rolls. I'm not doing it neatly, but I've done it neatly again in your solution set, okay, or in your notes. Okay, so the probability of 3 sevens in a total of 10 rolls is 0.1550. But remember, there's all kinds of other things. I could get 0 sevens, I get 1 7, I can get 2 sevens, 4 sevens, 5 sevens, 6 sevens, 8 sevens, 9 sevens, 10 sevens. I probably missed something. The whole point to all that is I could get all those situations. This is just that one event, and it's 50.5% likely. Okay, which is a pretty high probability given that situation of 10 different outcomes, because it's obviously not evenly spread out. Okay, and that's really what an expected value is. We'll do an expected value for our next example. So for our next example, for an expected value, we'll do a calculation first, and then we'll do our expected value. Again, we're working our way through this. So a basketball player scores 85% of his foul shots. First things first, repeated trials? I don't know, we have to go further. If he has 8 foul shots, okay, repeated trials? Yeah. 8 foul shots, 8 trials. Okay? What's the probability of scoring 7? Okay, now, this is a key feature. If you're a basketball player, you're not going to agree with me, but that's okay. I understand. Independent or dependent events. Does the probability of getting a basket stay the same each time? I know any basketball player is going to say no. It's completely situational. It depends how tired you are. It depends on all kinds of different factors. Okay, but sometimes when we do these problems, we have two situations we roll into. One, we have nothing better, so we have to assume it stays the same. And on average, it should be the same. Or two, what we're going to be using this stuff for eventually in university is we're going to be looking at this and seeing the deviation from this. So we always want to do it assuming it stays the same. And then we will compare it to what it actually is and use what it is we know about the situations, some causal factors or some variables, extra variables that play a role in explaining why his foul shots weren't as good or were good or better or whatever. Okay, and there's actually hypothesis testing designed in order to do that, but you're going to do that in university. Okay, so if he has 8 foul shots in the game, what's the probability of scoring 7 of them? Is the probability independent? We have to assume that it is. So in which case, what's a successful? Probability of scoring 7, I'm looking for scoring. So my probability is scoring, 85%. My failure is just 0.15, certainly easy to go along with that. Okay, because of course it always adds up to 1. And then am I looking for a specific number of successes? In this case, I'm looking for 7 successes, scoring 7. So I'm looking for P at X is equal to 7. I'm looking for probability of 7 successes. Okay, so I have my 7 successes. I have, of course, my 1 shot that I miss. My 7 successes, 0.85. My failures, 0.15. And then I have my choose. But you don't even need to do this choose if you don't want to. Because if you're hitting 7 out of 8 foul shots, that means you have 1 foul shot that you're missing. Where that 1 goes could be in the first spot, the second spot, the third spot, the fourth spot, the fifth spot, the sixth spot, the seventh spot, or the 8th spot. That's only 8 different times, different ways. So it's this or 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 this. This is going to calculate it. And then we have to add it together 8 times or multiply it. What do we multiply it by? The choose. If you don't want to think, the choose does the thinking for you. 8 trials, 7 successes is what I'm looking for. 8. Now, I'm not even going to calculate this for you. I'm going to leave you guys to look at the notes and calculate it and maybe even try it out yourself to see if you can get it with all the decimal places included. Okay, and again, therefore, probability of scoring 7 of 8 is 0.3847, or about 38%. 38.5%. Okay? The next thing that we're going to use, of course, is an expected value. Super easy to do, NP. Okay? And it just involves the number of trials and then the probability of success. Obviously, each trial you do, there's going to be an 85% chance of being successful, and that 0.85 for each trial will add up a number of times. In this case, of course, it's going to add up 8 times because there's 8 trials. So it's 8 times 0.85, which means it comes out to 6.8, which means you would expect the player to score 6.8 shots out of 8. It has to be out of 8 because, of course, if you include more shots, then there's going to be more or less shots that you would expect them to make. They do less shots that you expect them to make, and so on. But if that probability stays the same, that's what it is. Now, that's an average expectation. If he deviates from this expectation, if he gets all 8 shots in, he's having a good game. Maybe he's hot. Maybe he's in a streak. If he gets 4 or 5 in, then maybe he's having a bad game. Maybe he's injured. Maybe, I don't know. Maybe he's having an argument with the coach. Who knows what it is? He's not in his game. But either way, you can test it based on this expectation. Okay? Our last example is an example of a question with a distribution. Okay? So this shows us how to do a full distribution, which means all outcomes. If I did a distribution for this guy, I would have to do 0, 1, 2, 3, 4, 5, 6, 7, and 8 shots in. Because all of those are possible outcomes when I'm doing repeated trials. I could have from 0 successes all the way to, I think this was 8. 8 successes. Okay? And that's what I'm doing here. Now, I've made it smaller. We're not going to do 8 trials. We're only going to do 4. Okay, but this also has another issue. So first of all, we're going to do a probability distribution, which is all of the outcomes. In this case, we were doing 4 trials, and I'm just going to do it ahead of time. So what does a distribution look like? Oops. You have X. That's always the number of successes. And then you have P at X is equal to X, and that's the probability of success. Okay? And so in this case, if we're going to do 4 times, we can have 0 successes, 1 success, 2 success, 3 success, 4 success. Okay? That's the way a distribution is going to work out. That's one theme for this question that's important. Another theme for this question that's important, just want to make sure it's still taping, that's important is the idea of independent versus dependent. Let's look at this situation. Okay, a card is selected from a deck and its value recorded and placed back in the deck. This process is repeated a total of 4 times. Calculate the probability distribution for the number of face cards selected. All right. You and I know that the examples that I used for you guys for cards were dependent. When you take a card out of the deck, the number of cards in the deck changes, and of course the number of possible successes may or may not change. But either way, the probability is going to change. This is not dependent when we're using cards. But don't be a robot. Okay, we're using cards, but we're turning them into kind of like dice. Okay, it's selected from a deck of cards, value recorded, and then placed back in the deck, and then shuffle, shuffle, shuffle. That means the probability of a king is 4 to 52 the first time. I take a card out, I record it, king, I put the card back in, shuffle, shuffle, shuffle. The probability of a king is still 4 to 52. When you're choosing from small groups like a deck of cards, you almost default to dependent events. Dependent events are ones that change and they're noticeable. But if you were to take 1 billion cards and spread them all over a table or something like that, or stack them in a huge deck of cards and randomly choose from those, then the probability would pretty much stay the same. And this is a debate that we're going to have for next unit. If you have a small group that you're taking from, the probability changes. If I'm taking from people in our classroom, males and females, and a male is a success and a female is not a success, or not a male is a success. Anyway, if I'm choosing a group of 5 people from a classroom, the probability changes each time I take a person from that classroom of 27 students. But if I'm taking people from Ontario's population, or even our school's population of, I think, about 1,100 students, if I'm taking 5 people from that, does the number of men and women really change? I mean, it changes, yes, absolutely, but it changes by what's called a negligible amount. So in that case, we would treat it as independent. So there's a bit of thought that's involved in this process. So it's going to be you working through these ideas and these situations and making decisions based upon them. In this case, it is most definitely, even though we're using cards, we're putting them back in the deck so the probability stays the same. Okay? And that's the situation I wanted to talk about along with the distribution. The process is repeated 4 times. So we're doing repeated trials. Okay? We've already established that it's independent, even though it's cards. Okay? Because we're putting them back in and we're shuffling them. Now what we're going to do, sorry, I'm making sure it's taping. Now what we're going to do is we're going to see what a success and a fail is. Okay, so let's finish reading the question. Calculate the probability distribution, that's this, all of the outcomes, for the number of face cards selected. Okay, so my probability of success is going to be, well, it looks like face cards. So face cards, there's Jack, Queen, King, 4 suits, 12 out of 52, which reduced is 3 out of 13. Q, I don't have to do any work with that. I just go 3 to 13, what's left? 10 out of 13. Simple. It's like odds. Really easy. Okay? And then what do? Then I do my calculations. Now, usually I go around and I look, oh, am I looking for like 3 face cards or 2 face cards? Or what? No, I'm looking for a distribution, which means I'm looking for the probability of 0 face cards. That's one outcome that's possible. 1 face card, 2 face cards, 3 face cards, 4 face cards. That's why this is a discrete probability distribution unit, because the outcomes are discrete. Specific. Only specific values are allowed. Successes, you can only have 1 or 2 or 3 in reality occurring. Okay? So as a result of that, then we don't tend to have any decimals in these, and of course it's a discrete probability distribution. Okay, so let's go ahead and do this. This is a good way to practice our formula. Okay? So I want to do P at X is equal to 0. So that means I have 0 successes, 0, and I have, how many failures? 4 failures. Got a total to 4. Okay? Then I've got a choose that goes along with this. So my success is 3 out of 13. My failure is 10 out of 13. And then I have a choose that goes along with it. Okay? That choose that goes along with it is just going to help me determine how to do that. But if you look at this, of course, to have 0 face cards, there's only one way to do that. But we use the formula just to be sure for choose 0. As a result of that, we're sitting in a situation where we have our calculation. I'm not going to do the calculations. I've got it for you in your notes. You can go ahead and use it as a practice if you want to. I'm going to go P at X is equal to 1. Okay, that means we're going to have 1 success, 3 failures. Again, write down the success, write down the failures, and for the choose, you can again reason this out. If I have 1 success, I could have face card the first time, the second time, third time, or the 4th time. There should be 4, or 4 choose 1. P at X equals 2. 2 successes, which means we have 2 failures. Again, we can do 3 out of 13, 10 out of 13. And then for our chooses, we've got 4 that we're choosing from, 2. A little tougher for you to figure out of those 4 the number of ways in which you can do it, but you could if you wanted to. You can go face, no face, face, no face, 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 no face, no face, no face, no face, 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 no face, face, no face, face, and then no face, 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 no face, and then face, no face, no face, face. I think that's 6 of them. Anyway, whatever. If I miss them, oh well. Or if I double counted, sorry about that. That's the beauty of this. You don't have to worry about it, okay? The probability again of 3 successes. So we're going to have 3 successes, 1 failure, 3 out of 13, 10 out of 13, and then 4 choose 3. Okay, we know that there's only 4 ways that can happen, but again, I'm not going to go over that. You guys can go over these ideas and watch the video multiple times if you need to cement that understanding. Probability of having 4 successes, no failures, 4, choose 4. Oops. Getting ahead of myself, getting in the groove. Okay, try not to follow the pattern, try to reason it out each time. It's good practice, gets you used to the formula. Your homework is actually not this unless you want to do the new textbook. If you want to do new textbook homework, you can do that one. But otherwise, I've got the only homework that I have set out for you is the old textbook. Okay, so use the old textbook and go with that. If you want to use the new textbook, go with that. If you have any questions, let me know.